Okay, so the idea now is that we want to talk about a unitary matrix. When we're talking about a unitary matrix, we are talking about a matrix that its columns are orthonormal to each other. So if I say unitary matrix with example, I will get a matrix that each column is orthonormal to one another, namely the inner product between the columns equals to 0. So if I say the columns of the matrix, unitary matrix, are orthonormal, I wish it would give me also an example. So it will tell you yes. And if it will give me an example, so the inner product between any two columns is 0 if the columns are not the same, and is 1 if the columns are the same. So they are orthonormal to each other, and each column, its size, its norm is 1. So when you are talking about an orthonormal matrix, think about a matrix when every column is a vector that orthogonal to one another, and each vector norm equals to 1. And when we're talking about the definition of orthonormal matrix, the conjugate transpose times the matrix itself is I. Think about it, why it happens. Because the columns are orthonormal to each other. So when we multiply the columns, we get the identity matrix because it's just 1. And think about it like this, it will be easier. Now we have properties of unitary matrices. It preserves the inner product of vectors. It means that if I take the inner product, the unitary matrix with a vector, and another vector times the unitary matrix, it's like taking the the inner product between the two vectors without the unitary matrix. Also, it preserves size of vector. Namely, if I take a vector and multiply it by the unitary matrix, I just get the vector itself in regarding to the norm of the vector. Now, the determinant of a unitary matrix, its absolute size is 1, and the eigenvalues are again modulus 1. Modulus, not equals 1. Now, those are examples of unitary matrix. Again, if you take the multiplication between this column and this column, you will get 1. You'll get 0 because they're orthogonal, but this column times itself is 1. The same goes for this column. Now, if you take the conjugate transpose, you get this, and if you multiply them, you get the identity matrix. This another type of orthogonal matrix. Now we're talking real, the field of the real numbers. We're talking about orthogonal matrices. And if you look at this matrix, usually those are the rotation matrices. So if you look at this matrix, again, you will take the inner product of this with this one, you will get 0. And now we are in the real field. So this is, instead of conjugate transpose, we're just taking the transpose. So if you take the matrix transpose matrix, we are getting I. Now, if I ask him, when we are talking about, or if I'm just asking this, when we are talking about orthogonal matrix, namely in the real field, so each column vector norm is equal to 1, like in unitary matrix, or not. So I ask him now about orthogonal matrix if still it's orthonormal columns. I mean, each vector column is still equals to 1. And it tells me that the answer is yes. It means that, again, what we saw in unitary matrix, that the inner product between two columns of the matrix equals to 0 if this is not the same column, and equals to 1 if it's the same column. Namely, each column is a vector with a norm of 1. So it's like orthonormal. Here it gave me the property of a unitary matrix in the complex space, and orthogonal matrix, this is the parallel matrix in the real space. Again, this is the property. This is the inner product. The norm is 1. Orthogonal, yes, and preserve vector norms. It preserves the norm of the vector. And the determinant is modulus 1, and here is plus minus 1. Okay, so this was about unitary matrix in the complex space and orthogonal matrix in the real space. And we saw some examples and the idea. In the complex space, we're talking about a matrix when we're talking, and the definition based on the self-conjugate is conjugate transpose, and in the real space, we're talking about the transpose of the matrix. Again, the norm is 1 and everything, and that's it. Preserve the norm, preserve the size of the vectors, preserve the inner product, as we saw. Thank you very much. So this was about a unitary matrix in the complex space, and orthogonal matrix in the real space, and the properties and the definitions of each one of them. Thank you very much. If there are any mistakes or correction, please tell me. Thanks for ChatGPT that really fast create me the things that I wanted to show. Thank you very much, and that's it.